So on page 1 of your books, it is going to be labeled Parent Graphs of Trig Functions. So again, it's going to kind of serve as a reference for all of the trig functions that we're going to deal with in this particular unit. Okay, this unit 6 of trigonometry part 2. So we're going to start off with the basic sine function. So go ahead and open up where it says y equals sine x. We're going to basically fill this in. Okay. Now the graphs of sine and cosine and tangent, etc., they can all be derived from your unit circle. Hopefully you haven't forgotten your unit circle between your midterm and now, because we are not done with it. Okay? You can always create the graph of sine by relying on the good old t-table, except the x values are going to be the radian measures, and then the y values are going to be the actual, value when you plug it in. So if we have y equals sine x, okay? And we plug in pi over 4. What's the sine of pi over 4? Who remembers? Sine of pi over 4. Say again? Radical 2 over 2. Now this definitely is not a whole number, is it? No, okay? And I'm not really trying to pull out the calculators or anything like that, so let's go on to the next one. What about when it's pi over 2? What is the sine of pi over 2? 1. Hey, that's the easy one to grab. Go ahead and plot that point. At pi over 2, I'm going to be at a positive 1. What about 3 pi over 4? When x is 3 pi over 4, what's y going to be? What is the sine of 3 pi over 4? Well, it's not negative, because think about it. It's going to be positive because you're right here. You're in the second quadrant. And sine is still positive there. Again, another number that I don't know the decimal to, so I'm just going to skip it. Go to the next one. What about at pi? What is the sine of pi? 0. That's another easy one for me to graph. So at pi, I'm at 0. What about 5 pi over 4? What's the sine of 5 pi? Negative root 2 over 2. Very good. Again, another decimal I really don't know. I'm not really concerned with that. Let's keep going. What's the sine of 3 pi over 2? Right there. Negative 1. Another nice one. So at 3 pi over 2, I'm down at negative 1. 7 pi over 4. Not a nice number. Let's keep going. What's the sine of 2 pi? 0. Okay. Now, I don't know why this chart did not include 0. But let's do it, okay? What's the sine of 0? 0. So there we go. Let's connect these points and make a smooth curve. Don't make V's now. Try to make a smooth curve to connect all those points together. And that, ladies and gentlemen, is the graph of sine. Okay? Nice smooth curve. Now, of course, sine is not, it doesn't start at 0 and end at 2 pi. It does keep going after that. You remember your coterminal angles and things like that? Those also continue to go. At negative pi over 2, what direction am I moving along in the circle? Is that clockwise or counterclockwise? Clockwise. So if I go clockwise to negative pi over 2, what is the sine of negative pi over 2? Negative 1. Continue in that direction. What about a negative pi? What's the sine of negative pi? What is it? 0. Keep going in the clockwise direction. What is the sine of negative 3 pi over 2? Positive 1. And then negative 2 pi. What's the sine of negative 2 pi? 0. If you notice, isn't there a pattern? And of course, I'm only using 0, pi over 2, pi, 3 pi over 2, and 2 pi to graph the points because they're nice and pretty numbers. Okay? Nice and pretty numbers. And there you go. That is the graph of sine. But does it stop at negative 2 pi? It keeps going, right? What about after 2 pi? Does it stop at 2 pi? No. So what is the domain of your sine function? Negative infinity to positive infinity. Very good. about the range? What is the range of this function? Look at that paper. Look at your paper. What would you say the range is? Are they included?
Yes.
Yes, they are. Because clearly it goes up to 1 and down to -1. Now, these next two words, okay, might be something a little bit new to you guys, but the amplitude, which we're going to talk about a little bit more for your sine function, is 1. Amplitude. Is anybody, you've heard the word amplitude before, yeah? In reference to what? Sound, right? Sound waves. So amplitude is what? Somebody tell me what amplitude is in regards to like sound music. The maximum wave, okay?
Isn't it like from the middle of the wave to the top of it or something like that?
Mm-hmm. The amplitude is basically from the middle of the wave. So like when you're sitting at like 0 and then you crank it up to the highest that it can go. So from the middle of the graph to the top, that is your amplitude, okay? So the distance from the middle to the top is 1. Period. The word period, which we'll talk about a little bit more in detail in the future, for your sine function is 2 pi. Your period is 2 pi. Period relates to the length it takes for the curve to repeat itself, okay? If I start at -2 pi, I can go up, then down, then I'm back here, and then the graph is going to start to repeat itself and continue to repeat itself every 2 pi radians, okay? Period is 2 pi. Zeros, that's an old word. What does zeros mean? X-intercepts. What are the x-intercepts for the sine function? 0, pi, 2 pi, -2 pi, but since it keeps going, what do you think other zeros are going to be? 3 pi, -3 pi, 4 pi, -4 pi. It's going to keep going, isn't it? So how would I represent that? How would I represent my zeros then? How could I represent my zeros? So I can't just list them all out because that's impossible because they keep going. No? We did this a long time ago, like unit lesson 1. It did deal with set and interval notation. How do you represent 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi and 6 pi and 7 pi and 8 pi and 9 pi? No? It does involve element. Ooh. So how do you represent all the multiples of pi? Pi n is every pi. And n has to be a what? Well, natural talks about your positives. Can't this also be negative? So it's actually going to be which ones? Integers. So we'll say it really quietly. So pi n, and n has to be an integer. Ooh, lesson 1. Throwback. Yes. So math builds on top of itself. Absolute max. We talked about that one back in lesson 3. It is 1. The highest that it can go. What's the absolute min? -1. And those are your properties of your sine function. You got a nice curve there. Bada bing, bada boom. Questions on sine? Let's look at cosine. I want you to go ahead and fill in the table, and I want you to, if you're using pen, I will probably try to switch to a pencil just in case you make a mistake. But I want you to fill in the table just the same way we did for sine, but this time you're using cosine, and then I want you to graph it. Remember, you're asking yourself, when you have pi over 4, what's the cosine of pi over 4? And I want you to complete the table and graph it. About 2 minutes. All right, let's run through this really quick. What is the cosine of pi over 4? Square root of 2 over 2. Yes, Caleb, what's the cosine of pi over 2? 0. Luke, what's the cosine of 3 pi over 4? Awesome. Chris, Christian, what is the cosine of pi? Awesome. Kaylee, 5 power 4, what's the cosine? Wonderful, wonderful. Nicholas, what is the cosine of 3 power over 2?
0.
0. Seth, 7 power 4. Awesome. Alexis, 2 pi. 1. And I know it's not there. Why? I don't know. But what is the cosine of 0? Donnie?
1.
It is 1. So when you connect those, you have 0, 1. The next nice one I'm going to graph is pi over 2, 0. The one after that is pi negative 1, 3 pi over 2, 0, and 2 pi positive 1. A nice smooth curve connecting all of those. Now, one thing you'll notice as we're doing these graphs, my sine curves will always look so much better than my cosine curves, so 0 judgment. Yes? Yes. All right, let's do the other side. Anna, so if I kind of continue that pattern going backwards and using my unit circle, if I go to negative pi over 2, what's the cosine of negative pi over 2? It is 0. And if I keep going, E sine, what is the cosine of negative pi? It'll be negative 1, yes. And if I keep going, negative 3 pi over 2, Monica, it is 0. And Michael, negative 2 pi? Is positive 1. Very good. Now, I'm using these. I'll refer to them occasionally as the big 5. Because when we do other types of graphs with this, those are the easiest ones to manipulate and to use. And there you go. You have your graph with cosine. What's the domain, you think? Aiden, what do you think the domain is?
Domain?
Yes.
All real.
It is going to be all real numbers. Give me good time to review set notation. How would I write that in set notation? Exactly, yes. What is the range here? What is the range,
Wait, I
Tanner?
have a question.
Oh, question, yes.
When you go into the negatives, how are you supposed to plug it in? Like,
Well, you're still using the unit circle in the sense, but you're going in the clockwise direction. That's why I don't know if anybody looked up whenever I did this, but when you're going in the clockwise direction, negative pi over 2 is just 90 degrees, so it's a quarter of the way. So whatever that order pair was when you went counterclockwise, it's still the same order pair when you go clockwise. So this is still 0, negative 1. This point over here is still negative 1, 0. This point here is still 0, 1, and so on and so forth. So when you're going in the negative direction, it's still those same ordered pairs. You just need to know that you're going negative 90 degrees, negative 180, negative 270, going in quarters. But Tanner, the range? Included or not included? Very good. And the amplitude. Anyone?
1.
It is still 1. The period. How long does it take before the graph repeats itself? 2 pi. A lot of similarities with sine. However, the zeros are different. When you agree? Looks like we have zeros occurring in negative 3 pi over 2, negative pi over 2, positive pi over 2, 3 pi over 2. How do you represent all of those zeros? Multiply what by pi over 2? And how do you represent multiples of pi over 2? He's right, it is multiples of pi over 2, but it will be what?
Pi over 2n.
Pi over 2n. And n is a what? All integers, yes. Is that right? Think about it. If I plug in 1, does it work? Is that a 0 when I plug in 1? When I plug in 2, does that work? Is that 0? So when I plug in 2, that doesn't work. But when I plug in 3, it works. When I plug in 4, does it work? Okay, how do we represent that? How do we represent all the odd integers? Okay? It has to be all the odd ones. We can't just say n is the element of integers, only the odd ones. We can't say that. Okay? pi over 2. And what do you think the next one's going to be? And what do you think the next one is going to be after that? What are you doing? What's the next one?
Plus pi over 2.
Plus 2 pi.
Like we're almost. What is it?
Plus pi.
You're adding pi every time. That's how you're going to each one. So it's pi over 2n plus pi. Those are your zeros. Those are your zeros. Absolute max. Who did I call? I called it. Who did I have? Yes. Volunteer. Yes, Miss Casey. It is 1. All right, the absolute min? -1, yes. Those are your properties of sine and cosine. We'll start with those, okay? We'll start with those, yes.
Can you tell me how you got the amplitude?
Mm-hmm. Okay, the amplitude, which we're actually going to talk about in like the next slide. But the amplitude is basically the distance from what's known as a midline, a center line, like an equilibrium line, to the highest value or to the lowest value. And so essentially when we're looking at sine and cosine, the x-axis is that equilibrium. And the distance from that dotted green line up to the max is 1 unit, down is 1 unit. And then again, the period is the distance it takes for the cycle to repeat itself. So we start here. It will repeat itself after that point. Just 2 pi. Questions before we keep going? All right. So flip over to page 2. We're going to come back. We are going to complete tangent, cotangent, all the other ones at a later date. Okay? Let's go ahead and swing over to page 2. There is your title. We're actually going to get into the notes for today now. The goal is to graph transformations of sine and cosine functions. We have the basic ones now. Now we're going to look at the ones that are a little bit more complex. That is your page title. Please make sure you always write down the goal as well. All right, so we are going to write some, okay, before we get to the next foldable, okay? But when what we're going to graph to start are your sine and cosine functions. That's why we spent some time on them. But both sine and cosine functions are known as sinusoidal functions. Reason why? Both have the shape of a sine curve. You notice both sine and cosine, they model each other. They really do. And these are the general forms for sine and cosine. Now, A, B, C, and D all have some type of effect on the very basic graphs of sine and cosines, the ones that you guys have graphed on your on that goldenrod color sheet. Today we're going to be talking about what A does to the graph and what D does to the graph. The next class period we'll talk about B and C. Okay? So again, A, B, C, and D all affect the graph in some shape, way, or form. And in actuality, you guys have actually done these different things to graphs in the past, such as quadratics and radical functions and cubic functions and absolute value functions. Where am I going with this? What concept am I talking about? It did deal with your parent function. Transformations. These are different types of transformations to the graph. The number right here that's on the outside, when you add it, or down. When it's on the inside, it what? Left or right. The opposite. So if it was a positive, it moved to the negative, it moved to the right. What did the number out front of the function do? Stretch or shrink, which way? Vertically or horizontally? Vertical. And B, by a factor of the reciprocal, the inverse, 1 over that number. You guys haven't forgotten too much, okay? To be honest, I don't want you to write these down unless you legitimately forgot them, okay? Remember, if it's on the outside, being added is what again? Up if it's plus,
Oh, down.
down if it's minus. Again, you do not have to write this unless you legitimately do not remember. When the number's on the inside of the function, and it's a plus, minus, good stuff. Okay? When there's a negative on the outside, you guys remember what the negative did? Reflection over the x. Which meant that this one had to be what? Very good. When there's a number on the outside, which one was it? By a factor of what? The number. What if it's on the inside? By what? So, okay, all this is definitely going to come in handy when we are graphing, okay? So these were all from transformations back in like what? Unit 1, Unit 2, page 15, okay? Let's describe some of these transformations to the sine and cosine graph. Yes, get these examples down in your notes. We're going to describe these different transformations. All right, so here we go. Describe the transformations. Who got the first one? Raise hand. I'll take volunteers on this one. Who got the first one? Describe the transformation. We'll start y'all probably seriously. Wow. Cosine, yes.
Horizontal.
5. All right. So you should have went your first instinct. It was vertical.
What's vertical?
It was a vertical. And it ends by a factor of 1/4. That's why I want you to keep going. Okay? Because it's on the outside. You can say shrink, but I wouldn't count you off if you said shrink. I'm more concerned about the vertical and then the number. Okay? What about B? I'll take a volunteer on this one. Malaysia. Reflect over the which axis? It's actually going to be over your x-axis because since the negative's on the outside, remember that's basically like you're making your y's negative. The only way to do this is go over your x. But this 3 does something as well.
Right.
It's a vertical by a factor of what? By 3. Yes, so remember, if it's on the outside, it's reflected over your x-axis. If there's a number in front, it's a vertical stretch by that number, or shrink. What about C? Who's got C? Michael?
Horizontal stretch vector.
Very good. It is a horizontal stretch by 3. Remember, it's a reciprocal because x over 3 can be written as 1/3 times x. And since that number is on the inside, it is horizontal and it's the opposite. Who got D? I got 2 transformations. Christian, give me one of them. What's one of the transformations? No, opt out here. Help him out. Give him one of them. Which one you gonna say? It is a reflection over. You're making x negative. How do you make? You say f y. You're right. Okay, so she took the hard one. When there's a number on the outside. What does that mean? Look back here. Number on the outside. It is up by 3. Yep, up by 3. And the last one, 2 transformations.
Right by 1 and down. Left.
It's left 1. Remember, whenever it's positive, it's the opposite. So you use left, down 2. Anytime it's on the inside, it's always the opposite. Just like here, instead of being 1/3, it was 3. Here, instead of being to the right, it was to the left. Anything on the inside is the opposite. How are we with describing these? This goes back to Unit 2. All memories, because math builds on top of one another. Okay? Let's get to some graphing now. Okay? Got a foldable here for you.
Is this the next day?
Depending on how big you wrote, this actually might still fit on page 2, but we are going to continue into page 3 with this and the examples. So if you don't have enough space, you can put this on page 3 and then just use that extra space to put an example. Alright. So that general form y equals a sine bx plus c plus d. Okay, had you guys write this down before. A, B, C, and D all represent some type of transformation, but it also relates to, you know, actual like words that relate to the graph itself. The A, the number in front, it does affect the vertical stretch or shrink, which affects the amplitude. Okay, how high the graph goes, how low it goes, that is what that number is. The amplitude is half the height of the graph. Okay, if you look at your basic sine graph, the maximum point was what number? And the minimum was what? Negative 1. Okay? It's half the height. Well, from here to here, how many units is that? It's how many? It's 2 units. What's half of 2? 1. And that's the amplitude of your basic sine function, okay? This one here, if you look, the highest it is what? 4. The lowest it is what? How long is that? What's that distance right there? And what's half of 8? 4. Okay? So A is basically half of the height. You can also look at it like this. Take that equilibrium. Take that midline. What's the distance from here to the top? Or from here to the bottom? Okay? But it's the absolute value. It's the absolute value. So if it was negative here, what's the amplitude?
2.
It's still 2. It's a positive 2. That negative doesn't affect the amplitude. That negative causes the graph to what? Flip. It's a reflection, okay? So if A is positive, then it's still the same curve. It's just stretched or shrunk. But if it's less than 0, it's reflected over the x-axis. Okay? Now, a vertical stretch, does that affect the y's or does that affect the x's? The y's, okay? So amplitude affects the y's. And how it affects it is basically you're multiplying all of your y values by your amplitude. Every single one of those y values gets multiplied by that a value, whatever a is, okay? Now, if you're like, what do I mean by that? Well, let's take a look at that table from the very beginning, okay? You can't, I definitely want you to write this down. But what I'm about to do next, you don't necessarily have to write down. That's a multiplication symbol. Definitely write this down here. Like your y's get multiplied by a, okay? Now, if you look at that original table that we had, I'm only going to look at the ones that had the nice numbers. 0, pi over 2, pi, 3 pi over 2, and 2 pi. What's the sign of 0? You guys are going to be so fast at this by the end of this unit, huh? Is 0. What's the sign of pi over 2? The sign of pi. The sign of 3 pi over 2. And of 2 pi? 0. So, whatever a is, if we ever have to graph this ourselves, whatever a is, we're going to multiply all of these y values by that number. So, if I wanted to look at this one, clearly I see the graph already. Okay? But since my a is 2, if I multiply all of my y's by 2, what's 0 times 2? 0. There's that point, 0, 0. What's 1 times 2? Pi over 2, 2. Everybody see that? 0 times 2? 0. Negative 1 times 2? So I'm at 3 pi over 2, negative 2. And there's that point there. 0 times 2? And there you go. That's where those points came from. Okay? You basically are multiplying all of your y's by a. That's how you graph sine with the answer. Questions on that? So let's take a look at here. It says determine the amplitude and graph the following from negative 2 pi to 2 pi. So that's how we're going to graph it from here to here. What's the amplitude for number 1? It is 3. Remember, amplitude is the absolute value of A. So the absolute value of 3 is 3. And since it's a sine function, we know we're going to take all of our y's and do what to them? Not add 3, but multiply by 3. So I'm just going to make a quick table. And I know some of you guys are like, why do you keep making a table? It's so easy. I don't need to make a table. That's fine. But some people might like the table option. When we get to graphing all, 1, 2, 3, 4, 5 transformations, you might appreciate the table a little bit better. Real quick, we're going to start out with the basics. What's the sine of 0? Sine of pi over 2. Sine of pi. What's the next one? And the next one. So all of these y's are getting multiplied by 3. 0 times 3? 1 times 3? 0 times 3? Yeah, you're one ahead of me. The next one is? So those are the points that I'm plotting. 0, 0. Pi over 2, 3. Pi, 0. 3 pi over 2, negative 3. 2 pi, 0. I also like the table because when you graph this, you can kind of see a pattern. If you ever have to extend it beyond just 0 to pi, it kind of repeats the same pattern over and over again. Okay? And also for that, if it turns out to be kind of funky, then I kind of know where you might know where you made your mistake. Is everybody still with me? Smooth curve connect. Now I gotta go to negative 2 pi. So I'm gonna pick the next nice value, which is negative pi over 2. What do you think is gonna be the point that goes with negative pi over 2? Negative 3. It has to follow that same pattern. What about at negative pi?
0.
At 3 pi over 2, should be here. I don't know why it's not. It's gonna be a 3. And then 0. A little rusty. So, and I know you're like, I don't need to do a table to do this with Anderson. That's fine. Some people don't need to, okay? But it does make it kind of nice and neat if you ever ask me, hey, is this right? And I got to double check your work. It does kind of help me out a little bit, okay? I'm still using the same big 5. And since the sine is the same y values as before, 0, 1, 0, negative 1 and 0. But I'm going to multiply all of my y's by what number? Negative 1/2. So this is going to still be 0. This one's going to be a. This one? Keep going. So here it is. Boom. Here, 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 here. And as you can see, since it was 1/2, it should have been vertically shrunk, which it does, and it's reflected over. What about a negative pi over 2? Where are we? Positive 1/2. At negative pi? 0. At 3 pi over 2, which is not labeled again. Negative 1/2. And negative 2 pi? Easy stuff, right? I know this. Okay? Do we need another example? You guys think you got it? You got it? Okay. So then we'll move forward. We'll skip this example. Let's look at our vertical shift. So flip over to the next splat. Your vertical shift is what happens when when there's a number in the D spot, okay? Every point on the graph is shifted vertically by a value D. If D is greater than 0, it goes up. Less than 0, it goes down. But we already know this is the vertical shift. When you move vertically up or down. Does that affect your x's or your y's?
That's your Y's.
It affects your y's still. So when you have a vertical shift, you want to multiply by that number. That's the vertical shift. Add or subtract it. Okay. So with the vertical shift, you want to take your y's and either add or subtract whatever d is. Okay. This is for your vertical shift. And as you can see in this graph, you have the graph of regular sine. But because it was a plus 3, that literally meant all the points moved up 3 units, every single one. Question?
So you want us to draw 2 graphs?
No, you don't have to. If you do draw up the original graph and you use that to do your vertical shift, that's fine. But if you like to do the table and just give me the final graph, that works too. Okay? If I add 3 to each one of these, what's 0 plus 3? 1 plus 3. 0 plus 3. Negative 1 plus 3. 0 plus 3. These are the points that go along with it. 0, 3. Pi over 2, 4. Pi 3. You see how it works? It doesn't change. Does everybody see it? If it's a minus, it goes down. Look at that. There's 2 things happening here. Which one do you apply first?
The 3.
You apply the 3 first. You always apply any multiplications before you ever do any additions and subtractions. Same rules from before with transformations. So if you have a combined one, you do your stretching first, which means you'll multiply by your a first, and then you'll add or subtract the d to whatever result you get. Does that make sense? How is it? Is it pretty straightforward? Okay. I want you guys to do number 5. Just number 5. Do that now. What were my new points? I was at 0. My x was 0, my y was negative 2. If I subtracted 2 to each one, at pi over 2, I should have been at negative 1. At pi, I should have been at negative 2. At 3 pi over 2, I should have been where? Negative 3. And then at 2 pi, I should have been at what? Negative 2. Simple enough. And when I replicate that going over to this side, negative pi over 2, negative 3. And go down, continue that same pattern. At negative pi, negative 2. 3 pi over 2. Negative 1.
Okay, why would it be?
Huh?
I'm so confused on how to do that.
Alright, you gotta think, you gotta go in the backwards direction. Okay? So if anything, what might actually help here is for you to actually have a unit circle that goes in the negative direction. Because when you go in the negative direction, there's negative pi over 2. The order pair is the same order pair as it was before. 0, negative 1. This one here, you're at negative pi. This is still the order pair negative 1, 0. Going this way. Still the same order pair, but I've gone negative 270 degrees. I've gone 3/4 of the way. And this is still. Okay? So we're still just going in this, it's still the same set of order pairs as it was if you were going in the clockwise, counterclockwise direction. Okay? And also think, it has to be a smooth, continuous pattern. So if you're going backwards like this and then you go back up, it's not going to look like the same graph over and over. Yeah, like you'll be mixing cosine a little bit with it. What about this one for number 6? We got 2 things happening. What 2 things are happening?
Reflection over the x-axis and
Reflection over x and 3. So when I do this, I'm going to take my y's and multiply them by negative, and then add 3. So if I multiply all these by negative 1 and add 3, what will I get? What's 0 times negative 1? Plus 3? 1 times negative 1? Negative 1 plus 3? 2. 0 is going to be the same as this 0. Negative 1 1 times negative 1? Plus 3? And this 0 is the same as this one, the same as this one. So I'm at 0, 3. Pi over 2, 2. Pi 3. 3 pi over 2, 4. I'm a little off because I'm like looking at it. It's a little odd. And since it was reflected over, it should have went down, not up. That negative pi over 2 all would be a negative 1. What's negative 1 times negative 1? Plus 3 would be 4. So I should go up here because I reflected over. Then I should go where? To 3. This is really off. I'm sorry, guys. 3 pi over 2. And then 2 pi. I'm really struggling. Trying to look. Hopefully yours is a lot better looking than mine. I see I'm very much higher on that far side. You guys get my drift, right? Alright, so here's your first example that I want you to do with the grids that you just cut out. I want you to graph this one. Now, before any of y'all start gung-ho and everything, take a look. What's different from this one from the ones that we did already? It's cosine, which means that the table that you're going to use is not the basic 0, 1, 0, negative 1, 0. It's actually going to be what? It's going to be 1, 0, negative 1, 0, and then 1. So be aware, when it's cosine, these numbers do change, but the same way you apply your amplitude, your vertical shift, and your vertical stretch, you still multiply, but it's different numbers, okay? I'm going to leave this one up for about 2 minutes, and I'm going to switch to the other one I want you to do. Make sure you write down these equations. Okay, so here's the other one as well. Make sure you get down the equation, negative 2 pi to 2 pi. So your y's of 1, 0, negative 1, 0, and 1 should have been multiplied by what value? Negative 1/2, and then we should have added 1. So when we do that, 1 times the negative 1/2 is a negative 1/2, plus 1 is a 1/2.
Teachers, we have quite a few bus changes this afternoon that can
Here's the graph for this one.
student to ride 1261.